Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. We have been discussing about olefin polymerization. Particularly, we have looked into ethylene polymerization as well as propylene polymerization in the last few lectures, and there we have looked mainly into homopolymerization of these two monomers, ethylene and propylene. What it means that ethylene polymerizes to give polyethylene, and propylene polymerized to give polypropylene, and these are what is called this homopolymerization. Now, in the last class we have also looked into the other possibilities of doing copolymerization. Copolymerization can be of two different monomers. They can be both olefins like ethylene and propylene, ethylene 1-hexane or ethylene alpha olefins, and so on and so forth, or they can be of ethylene and alpha olefin bearing functional groups. Now, the main challenges which we have encountered is that these particularly for ethylene alpha olefin polymerization, the main challenges which was encountered was the rate of polymerizations are not the same for the two monomers. For example, for Ziegler-Natta catalysis as well as the metallocene catalysis, the ethylene homopolymerization is much higher at a much higher rate than the alpha olefin homopolymerization, whereas in metallocene catalyst the difference is not that extent. However, still it is less acute than the difference what is present in Ziegler-Natta catalyst, but still nonetheless they are there, that rate of homopolymerization of ethylene is higher than the rate of homopolymerization of alpha olefins. Now, when it comes to copolymerization of ethylene with alpha olefins bearing functional group, it is even more challenging because the heteroatoms of the functional group compete with the ethylene binding for which occurs at the polymerization site. As a result, the presence of functional group also poisons the catalyst for further polymerization, and this poisoning is more significant for a heterogeneous Ziegler-Natta type catalyst than it is for metallocene based bonds, and that is what was the main drawback, is that the polymerization of functional monomers were in fact poisoning the catalyst. However, nonetheless, in the last lecture we had seen this nice example where for zirconizing catalyst, Weymouth successfully homopolymerized heteroatom bearing functional groups. Like that it goes, and this is the repeat unit. So, the good thing is this was reported by Weymouth. Weymouth in 1992, and what this work is about homopolymerization of alpha olefins bearing functional group using metallocene catalyst. Using the catalyst, using the metallocene the catalyst, and these were isotactic, albeit in modest yield. Now, this is a interesting result, because this for the first time showed that for using metallocene catalyst, this poisoning of the metallocene catalyst with this kind of functional group does not happen that significantly, and one is able to obtain this homopolymerization of alpha olefin functionalized polymer in large yield. Now, that is a significant discovery, and that led to the discovery of an important catalyst which are called which are half sandwich complexes, and which are called constrained geometry catalyst. Half sandwich complexes of Cp metal amide types exhibited high catalyst activity for ethylene homopolymerization and ethylene copolymerization with alpha alkenes. Now, this was a interesting discovery, the Weymouth discovery way back in 1992, which sort of said that the metallocene based complexes are indeed tolerant towards functional group, and as a result further modification led to extremely active half sandwich complexes which showed very high catalyst activity for ethylene homopolymerization as well as ethylene alpha olefin copolymerization. Let me illustrate this with a particular example. Where R equals CH2pH, and here titanium is in +4 state, and this gives the following Me2Si nickel dibutyl titanium actually there is a activation of the methyl group as is shown here. And overall there is a positive charge, and the benzyl group is abstracted on boron which has a negative charge. So, overall this is a titanium 4 compound, but it is cationic in nature, and there is this anion and in the course of formation of this the first is the benzyl abstraction which goes on to boron as is observed over here, and the second is elimination of minus PHCH3, one benzyl group abstracts activates a methyl proton, the other one activates a methyl proton and eliminates as toluene to give this cationic complex. Now, these cationic complex is extremely a good catalyst both for ethylene as well as for polyethylene, which ethylene it could produce molecular weight greater than 10 to the power 6 Dalton and ultra high molecular weight polyethylene and with olefins it could do copolymerization. So, this is extremely good catalyst for polyethylene copolymer 1 hexene in greater than 30% yield. This is 30% incorporation and hexene less than 70% incorporation. So, extremely good catalyst for polyethylene as well as alpha olefin incorporation, and this catalyst is called constrained geometry catalyst. Constrained geometry catalyst. It has 3 features. The first one is electron deficiency. This species has total valence electron less than equal to 14. So, extremely electron deficient species. The second, there is a free coordination site. In presence of in vicinity of a growing polymer chain. And third is a positive charge complex, and this prevents suppresses deactivating dimerization. Dimerization process reactions and facilitates olefin coordination. So, these are very important notable features of this constraint geometry catalyst that is extremely electron deficient, then it has a free coordination site and also being positively charged, that it suppresses deactivation pathway and facilitates olefin bonding. And these are so good that it could produce ultra high molecular weight polyethylene polymer of about 1,000,000 molecular weight, huge molecular weight, and also it could produce ethylene 1-hexene copolymer with about 70% incorporation of ethylene and 30% incorporation of polyethylene. So, this is an important example, and this was reported by Marx, Professor Tobin Marx in 1997, extremely good catalyst. And the fourth feature of this is that it has a steric bulk. Fourth feature of this is it has a steric bulk that also takes care for this alpha high molecular weight polymer. This is illustrated just spoken about, and another important quality is that we had spoken about copolymerization of 2 units where this constraint geometry could polymerize ethylene as well as alpha olefin, and then a tar polymer or polymerization of 3 units. Important tar polymer is EPDM is obtained from ethylene, propylene and non-conjugated and non-conjugated diene. Example is 1,4-hexadiene. And these are polymerized by VOCl3 based Ziegler-Natta catalyst. As well as metallocene catalyst. EPDM behaves as an elastomer and is similar to natural rubber in properties. So, here we had spoken about in the previous slide we have spoken about the polymerization of 2 different monomers, one is alpha olefins and ethylenes, and then now we are talking about polymerization of 3 different monomers, one is ethylene, another is alpha olefin and non-conjugated diene, 3 different monomers. And these are can be done both as a heterogeneous way where it is used VOCl3 based Ziegler-Natta catalyst as well as by metallocene catalyst. These EPDM or the tar polymer are elastomeric in nature and behave similar like that of the rubbers. So, this is an interesting example where 3 different monomers could be polymerized to obtain something which is of natural rubber. So, in this regard another interesting property which we will be talking about is that of polycycloolefins. Now, they can be polycycloolefins can be obtained in two ways. Polycycloolefins can be obtained in two ways, and the first is important suitable. It should be a suitable catalyst to be chosen such that metathesis ring opening metathesis reaction is suppressed. And then this was reported by Kashiwa in 1988, and the reaction is given as follows. So, this the first is a Diels-Alder reaction. First is a Diels-Alder reaction to give this multicyclic species. As is shown here. And that in reaction with ethylene and VO Cl2 83Cl3 or metallocene catalyst gives this cyclic polyolefin, which is given over here of ethylene and ethylene over here, and what is seen over here, there are two things. First is the polymerization of the two units. One unit is this alpha olefin and the other unit. So, these two units are shown over here, this being the first These two units are shown over here, these being the first and these being the second ethylene unit, and this being the first. These two got copolymerized to give these polycycloolefins, to give polycycloolefin polymers, and the property wise important properties, they are thermostable, one is thermostable, the second is transparent, and third is minimally birefringent. Ringent and advantage over polymethacrylates and polycarbonates, and used for CDs, compact discs, and magnetic storage materials. So, these polycycloolefins again are copolymerization of two olefins, one is cyclic, another is ethylene, to give this, and they have important properties like thermostable, transparent, minimally birefringent, and also are used for CD and magnetic storage applications. So, with this we come to the end of today's discussion. In today's class we have looked into the copolymerization strategy of olefins and alpha olefins, and the main challenges arise in this area from two aspects. One is that the rate of polymerization of the two monomers, one is ethylene as well as the other is alpha olefins, are different, and it so turns out that alpha olefins are more slower than the olefins in terms of conventional Ziegler-Natta catalyst. However, in using metallocene catalyst, one can have a less acute difference of reactivity of alpha olefins as well as ethylenes. And what we have discussed today is about the advent of constraint geometry catalyst, which could produce ultra high molecular weight polyethylene of about higher than 1 million Dalton, and also it could successfully copolymerize ethylene and hexene with about higher incorporation, about 70% or greater incorporation of hexene and about 30% or so incorporation of ethylene in its copolymer. We have also spoken about going beyond polymerization of two monomers to polymerization of three monomers, and we have spoken about tar polymer from ethylene, propylene and 1,4-hexadiene, and then finally we have looked into polycycloolefins which are material of importance for magnetic applications. They are thermostable, transparent and minimally birefringent, and they are produced by two pathways. We have discussed one of them, which involves using catalysts that will not promote ring opening metathesis reactions, and hence first we have seen one example by Kashawa where first a Diels-Alder reaction and subsequent polymerization with OET Cl2 and presence of aluminum ethyl reagent or metallocene catalyst that could give these polycycloolefin polymers. So, with this we come to an end of today's class. More on discussion about various applications of these copolymerization with olefins and alpha olefins as well as with functional monomer as we continue the discussion in the next class. Till then, goodbye and thank you.